Hello, and welcome to our ELECOMP Capstone Fall 2024 Symposium virtual presentation. We are Team SEACORP, and our project is the Burst Learning Audio Spectrogram Transformer, otherwise known as BLAST. Our technical directors for this project are Bill Matuzak, the Director for Advanced Development at SEACORP, as well as Megan Chiavaro, an AI data scientist also from SEACORP. We also have Jamie Gagnon, a URI ELECOMP 2022 graduate who helped us as our consulting technical director. Our team consists of Jacob Porto, a double major in computer engineering and computer science, and myself, a major in computer engineering. SEACORP is a company that specializes in providing critical engineering solutions to maintain and expand the United States' maritime advantage. They are based in Middletown, Rhode Island, and work extensively within the naval defense industry to deliver services spanning across several domains. Some areas of expertise include the development of offensive and defensive combat technologies, the designing of cyber-resilient submarine systems, and the application of artificial intelligence and machine learning for automated signal analysis, this last point being the domain in which BLAST falls in. Our project is an applied research project in the sense that we want to explore the potential of using the audio spectrogram transformer, a relatively new machine learning model, for audio analysis. To understand the implications behind this motivation, we need to understand some background information. Many machine learning models developed for audio classification within the past decade have commonly used the convolutional neural network architecture. Originally designed for image-based applications, CNNs have been adapted for audio analysis due to their ability to process spectrograms, a visual representation of audio that resembles an image. While these models can perform well, they struggle in certain areas, notably in computational efficiency, model complexity, and the ability to capture the global context of data. This final point is especially important since in certain audio applications, such as speech recognition, only understanding a short clip is not enough to understand the full picture. Now introducing the AST model, which is the first convolution-free model for audio classification. This model utilizes the transformer architecture, which is a powerful architecture often utilized for generative models like ChatGPT. However, since the AST model is used for classification instead of text generation, only half of the transformer is used. Without the reliance of CNNs, the AST model is capable of outperforming its predecessors by improving computational efficiency by having data be processed in parallel, leveraging the parallel computational power of the GPU, achieving good performance on less iterations of training, and by learning important connections during training thanks to the self-attention mechanism of the transformer architecture. For our anticipated best outcome, we want to fine-tune an already trained AST model for a specific audio classification task. Classification meaning a model that is capable of analyzing an input and identifying what it is. We also want a model to have good performance, which will involve adjustments such as hyperparameter tuning and evaluation. In the end, we will create a portable demonstration that SEACORP can use during conference meetings to demonstrate the effectiveness of this new model in the audio domain. As mentioned previously, one of the main objectives of this project is to explore the effectiveness of fine-tuning an AST model for new audio-related tasks. Achieving this has the potential for widespread improvements across several areas. For one, further research and work into the model can create avenues for improvement on current systems and products related to audio/acoustic analysis, leading to increased customer satisfaction. There is also the potential for developing new innovative products or services by introducing this technology to new domains, such as anomaly detection or sound event localization. Finally, by creating a portable demonstration for conferences, SEACORP can use this product to present to investors, potentially securing additional partnerships and contracts. For our team's technical accomplishments so far, we have conducted research on the AST architecture as well as the general deep learning workflow, learned several signal processing techniques, especially those relevant for generating and manipulating spectrograms, looked into datasets with considerations for licensing and fair use, developed a working prototype AST model, found a suitable training environment for the model, and evaluated and improved the model's performance using several metrics. The following is a simple diagram of what the final outcome will look like. We will have some audio receiver capturing audio and pushing it into the actual machine learning model, after which the model will produce some classification with which some output handler will use to demonstrate to people. For this semester, we focused on developing the model itself. The following is a simplified workflow of our current prototype model. We begin on the left, which takes in an audio input, likely as a WAV file. And at this point, the audio is represented as a waveform, which moves through the pre-processing step. This step involves preparing the waveform into a form suitable for processing by the AST model, after which the AST model trains on said input to eventually produce a classification. For my individual technical contributions, I focused on several areas. First, I did research on the AST architecture and signal processing techniques. I also helped implement a pre-processing pipeline for converting raw audio data into the input format required for the AST model. Lastly, I implemented data augmentation, which is important for improving the model's robustness. To begin, WAV files are one of the more common formats for storing raw audio data and is likely how the audio receiver will pass data into the model. WAV files store raw audio data as waveforms, which represent the change in the magnitude, or loudness, of an audio signal over time. For a model to actually process the data, it needs to be transformed into spectrograms. This process involves several steps and makes up the pre-processing step of our model. Starting from a waveform, you would apply the short-time Fourier transform, which in short involves segmenting the waveform into windows along the time axis, applying the Fourier transform to each window, producing a composition of the frequency at each time step, and combining the resulting compositions into a spectrogram. As a result, we get a visual representation of audio with time on the x-axis, frequency on the y-axis, and the magnitude of each frequency at a given time as colors, where brighter colors indicate a higher magnitude. The final step involves converting the spectrogram into a Mel spectrogram. This is necessary as the Mel variation highlights the audio features that are perceptually relevant to us humans. This is because we perceive pitch and loudness on a roughly logarithmic scale. We get this by applying the Mel scale on the frequency axis and converting the magnitude spectrum to a logarithmic power scale. This modification makes it so the lower frequencies are emphasized, which is where the more meaningful information is concentrated. At this point, the audio data is in the correct format to be pushed into the AST model. For my other contribution, I implemented data augmentation. Data augmentation is a process of adding transformations to your data before passing it into the model, and is important in machine learning for the following reasons. For one, it reduces the chance of overfitting, which occurs when a model learns patterns or details that are specific to the training data, but are not generalizable to new, unseen data. It's like memorizing the exact answers on a study sheet instead of understanding the broader concepts. When faced with new questions that differ from the study sheet, you're unlikely to perform well. It is also a great way to address limited data, especially since it's often difficult to gather high-quality audio data in large amounts. Finally, augmentation is great for increasing the model's robustness, making it more tolerable to real-world distortions like background noise. There are several ways to go about implementing augmentations to audio data. We went with two different approaches, augmenting the raw audio data and augmenting the Mel spectrograms in a process called spec augment. Some of the augmentations for raw audio data we used include time shifting, pitch scaling, and noise addition. And using noise addition as an example, you can see how we modify the original waveform by injecting random noise into it. For spec augment, we included time masking, frequency masking, as seen below, where we mask or diminish bands along the x and y axis of the spectrogram. For my future technical contributions, I plan to research into potential audio receivers, taking into consideration digital signal processing specifications, such as bit depth, sampling rate, and the signal-to-noise ratio. I will also integrate the receiver into the AST model so the captured audio can be used for live inferencing. Lastly, I will also help with model evaluation and performance improvement.
Hello, my name is Jacob Bordo, and I will now discuss my individual contributions. My first contribution was creating a standardized method to transform .wave files, aka sound files, to Mel spectrograms. After this, I created a constructor for custom datasets. Finally, I created a binary AST classifier with evaluation. It is important to know how we implemented these technical contributions. First, we used librosa to import the wave files and convert them to Mel spectrograms. After this, we use PyTorch to deal with the handling of data within tensors, which we will get further into later. Finally, we have Hugging Face, which allowed us to import the initial AST models, create datasets, and fine-tune and train our model. First, we should discuss the standardized Bell spectrogram method that we applied. First, we defined the dimensions of what we want the Bell spectrogram to be. Now, this can either be done by the user if they want to fine-tune their own model, or be done within the code of a new model that the programmers will edit themselves. Either way, we need to decide on the X and Y dimensions. After this, we record the class of the audio file we will be putting in. The reason for this is that we want to know what the audio actually means. Now, for how we get this class, it can vary. It can be the file name, it could be the folder that the WAV file came from. Either way, we want to record that class. Next, we want to load the WAV file into the Python code. Now, the way we do this through Librosa is through a load function, and it takes the WAV file and stores it as a sample rate in audio time series. Finally, we use the Bell spectrogram function to put it all together. First, we set the X dimension by using the number of steps in the input of the Bell spectrogram. After this, we ceiling divide the size of the audio time series by the desired Y dimension. And by doing this, we'll be able to make it so that the Y dimension of the Bell spectrogram will be that exact same size. And then we load the audio time series and the sample rate into the Bell spectrogram function, along with the class that we will attach afterwards. After this, we return this combined set of Bell spectrogram and the recorded class. Now we will discuss the custom dataset functionality. Now first, you may wonder, why do we need a custom dataset? And the reason for it is this. Hugging Face, which we use to fine-tune our model, requires data to be in the form of datasets in order to work on. What this dataset requires is first, storage of features and targets independently. This is so that Hugging Face knows, okay, we are training on this, and our goal is to reach this. After this, we need to retrieve the length of the data, aka how many entries there are. This allows the model trainer to know, okay, this is how much I have to work with, and prevent any errors from occurring. Finally, we need to retrieve the data in the form of a dictionary. The reason for this is that Hugging Face can only receive the data for training in this format. After doing all this, our class looks like this: a custom data set with a feature tensor and a class tensor, which returns its length in the form of an integer and returns data in the form of a tensor, which has the feature and the class in the form of an integer. Now, since we've already discussed how AST model works, we should discuss how we evaluate it in the binary classifier. First of all, we use several different metrics. The first metric being accuracy, essentially how right a model's guesses are. In this case, this entire square is all of the data. The accuracy would be the true positives and true negatives added together divided by all the data points. Next, we have recall, how often the model correctly guesses the data when it sees it. Since we are looking for what's in the in the positive section, the recall rate would be the true positives divided by all of the relevant elements. Next, we have precision, how often a guess is correct for the desired element. Since we are looking for true positives, how accurately we guess true positives is the total of true positives divided by all types of positives, true and false. Finally, we have the F1 score. The F1 score is the harmonic mean between recall and precision, and this helps balance out the importance. Mean average precision is another method to do this, but it also takes account true negatives more. Now, let's discuss what our future technical contributions, aka what we want to do next, is. First, we want to develop a final model. We haven't gotten our final data set or what we want our final goal to be, so we should design that by next semester. After this, we want to train and improve our model via different methods such as pre-processing and improved hyperparameters. This will allow our model to be able to be better at the evaluation metrics we give it, such as accuracy. Finally, we want to develop a demonstration. A demonstration is important because it helps show people why our model is useful, why it is good. By doing this, we can get investment for our company. Now, let us reiterate on our final goals for this project. First, we want to develop a final model that will be worked on. Next, we want to improve this model via methods such as pre-processing and improved hyperparameters. Next, we will work on model evaluation and performance improvement, such as try to run it through GPUs more or find metrics that will be more accurate on finding what we want. Finally, we want to develop a demonstration to show our company and others that may be interested. Now, we do have risks to our goals. Firstly, issues with our input handler. If we have a perfect, absolutely perfect model, but we are using such a bad microphone that we are unable to get the data needed to show it's working, this is a major issue. Next, inability to fine-tune our model. If we're stuck getting accuracy rates of like 70%, that is going to be very bad for developing our model, since that's unacceptable in the workplace. Next, unacceptable delays in finding our final data set or developing our demonstration. We need a final data set in order to complete our project, and we need our demonstration to show our project. Missing these two things will cause major issues. Now, we'd like to take a moment and acknowledge all the people who helped make this project possible. First, from SEACORP, Bill Matsuzak and Megan Giovaro. They were both our technical directors and helped put this entire project together, telling us where we can find the information we need to help develop this project and making it possible. Next, from the University of Rhode Island, we'd first like to thank Jamie Gagnon, our consulting technical director. He lent us his industry knowledge to help put together the project and understand how to run things. Finally, we'd like to thank Professor Harish Sudak for being the director who put this whole program together.